Welcome to LIB Academy. In this video, I am going to take you through normalization of the wave function. What is the wave function and why are we normalizing it? And how do we normalize the wave function? The foundational equation in quantum mechanics are the Schrodinger equations. An example is a Schrodinger time-independent equation, where we have the kinetic energy part, the potential energy part of the particle at position x, and the energy value of that particle. If you solve this Schrodinger equation, you will get another equation or another function, and this function is called the wave function, usually of this form. So this is the wave function. Solving the Schrodinger equation to get another function which describes your system, and this function is also, is called the wave function. The way of solving the Schrodinger equation is there, but we are not going to be looking at that. The mathematical process of solving this to get the wave function start with first step, setting up the Hamiltonian operator, followed by solving the differential equation, and then applying the physical boundary condition. Now, what you need to know is that this equation is a second order partial derivative equation. Differential equation. So this equation is a second order partial derivative differential equation. So if you solve this, you can get several solutions, several wave functions, several solutions, which are the wave functions. And any solution that you get from solving this, when you multiply it by a constant, that solution turns out to be part of the solution. Multiplying by another constant will be part of the solution. Multiplying by a lot of constants will also give you a function that would be part of the solution. And I'm going to show you some simple mathematical problems here. This is what actually leads us to the normalization of the wave function. So we need to know why there is a need for us to normalize the wave function. This is a second order partial derivative, partial differential equation. If you solve this equation, the answer would be y equal sine x. So this solution, y equals sine x, if we multiply it by another constant, it will be a solution of this same equation. So y equal 3 sine x, multiplying by 3 will also be a part of the solution. Y equal 4 sine x would be part of the solution. Y equal 20 sine x would be part of the solution. To prove that, let's say from here we have y equal sine x. And we said if we multiply y by 2, that will also be part of the solution. So let's try differentiating this to the second order with respect to x and see what we get. So dy with respect to the x, respect to x, gives us what? Differentiating sign will give us cos. This is going to give us 2 cos x. Let's differentiate it again with respect to x. We are going to get 2 differentiating cos x will give us negative sine x. Sorry, this will be the second order. We first differentiated it, we are differentiating again. So d squared y over the x squared should be equal to, simplifying this, minus sine x. So now d squared y over dx squared will give us minus 2 sine x. But we already know that y equal 2 sine x is also part of the solution, right? Y equal 2 sine x is also part of the solution, which means that we can replace this whole thing here by y. But before we do that, let's try bringing everything to one part of the equation sign. We cross this over to become positive 2 sine x. So now we know that this same thing is the same as y. So d squared y over dx squared plus y equals 0. You will see that we are able to trace it back to the original differential equation. You see? So which means that y equals 2 sine x is also part of the solution. So as far as this one here is the first part of the solution, no matter the constant that you multiply by this, it would be part of the solution. So that is what you need to know about second order differential equations, partial differential equation. So this is exactly how the Schrodinger equation behaves. Solving the equation to get the wave function. That wave function, when you multiply it by another constant, it doesn't change the wave function, but it gives you a function which is also part of the solution. Now, keep this very well. We are going forward. Now that we know how second order partial derivative equations behaves, a scientist called Born proposed that if we solve the general Schrodinger equation and get the wave function, let's say psi of x, then the probability of us finding an electron in this, in the system should be equal to the absolute of psi of x squared. Born statistically interpreted that if this wave function is the solution of the equation, then the absolute square of this function should have something to do with the probability of finding an electron in the system. So if you solve the Schrodinger equation and you get a wave function psi of x, the square, absolute square of that psi of x should give us the probability of finding an electron in the system. But this wave function contains a complex part. The wave function psi of xt, let's say equals psi of x e to the power minus I e t over h cross. The wave function is complex. So if the absolute square of the wave function equal the complex conjugate of the wave function multiplying the wave function itself. So the absolute square of this is the same as this. So no matter what you see, whether it is written in this way or that way, or it's all about probability density, the probability of finding an electron in the system. So now this complex conjugate is a way of cancelling the exponential term out. We proved in our previous video, probability density is independent of time. So that is why you can just write the probability density as psi of x squared without introducing the complex conjugate of wave function. But any way that you write it is the same. So let's say looking at a particular space, we are to find the probability of finding an electron within the space which ranges from, let's say, x1, between x1 and x2, right? So the probability of us finding an electron within x1 and x2 can be represented as probability for us to find an electron between x1 and then x2, can be written as integral from x1 to x2 of the wave function. And the wave function, you can just write it with its complex conjugate, or like this. If you write it like this, it means there's no need to bring the square again. But if you are to just write in terms of the, I mean, this way, then you have to bring in the absolute square sign. So we are trying to get somewhere, and there is a need for you to know all this. That is why I'm trying my best to prove it this way. So this is the probability of us finding a particle between x1 and x2, right? Now, what happens if we must find a particle in the system? We must, that is if the particle exists. Then why can't we integrate from the entire space that a particle is supposed to exist? That is if the particle exists. Let's say from negative infinity to positive infinity. So Born then proceed with his statistical interpretation that if we integrate from negative infinity to positive infinity of the wave function, volume function. So in the entire space, if we integrate from negative infinity to positive infinity, the probability of us finding an electron, the probability density, it must be equal to 1. That is if a particle exists, because we are integrating throughout the entire space. So the particle must exist there. The particle must be there if it exists. And the probability of us finding the particle should be equal to 100%. Not 0.1%, which is 10%, 0.3%, which is 3, which is 30%, 0.8, which is 8%, 1, which is 100%. It should be 100%. That is if a particle exists. So now this is the Born statistical interpretation. The tau or the t here represent volume function. It could be the x, the y, the z, or all of them. That is if we are talking about Cartesian coordinates. Cartesian coordinates. But if we are talking about spherical coordinates, then our d tau should be equal to r squared sine theta, the r, the theta, and then d phi. Well, you need to know all this because it's very important. But we'll be looking at our calculation aspects right after here. Then, why were we looking at properties of second order partial derivative differential equations? So, this is what Born said. But there are some wave functions. If you integrate from negative infinity to positive infinity, you are generally not going to get to 1. So, what is happening? So, it means that you have to normalize the wave equation. Normalizing the wave equation simply means multiplying a constant by the wave equation, the wave function, and then looking for the probability density. That constant, when you evaluate it, that will be the normalization constant. So let's say this wave function here is not, when we evaluate it, we are not going to get 1. So we have to multiply, let's say we have a wave function psi of x. We have to multiply the wave function psi of x by a certain constant. Then we therefore take absolute square, and now the integral from negative infinity to positive infinity. If we do this, no matter how the wave is, it should be able to give us probability density of 1. So let's simplify this whole expression. So squaring this is going to give us integral from negative infinity to positive infinity n squared psi of x squared. So let's say the x here. The x should give us 1. So we want to calculate for the normalization constant. Because n here is a constant, let's bring it out. So bringing n squared out, integrating from negative infinity to positive infinity, psi of x squared dx equal 1. So we want to find the value of n, right? So why can't we divide the whole term by integral from negative infinity to positive infinity, psi of x squared dx? So doing so, we are going to get n squared equal 1 all out of integral from negative infinity to positive infinity, absolute psi of x squared dx. Now, removing the square sign, if we take square root of both sides here, we are going to get our normalization constant to be equal to 1 all on square root of integral from negative infinity to positive infinity, absolute psi of x squared dx. So if we find our normalization constant and we multiply it by the wave function, evaluate it from negative infinity to positive infinity, the value that we should get should be equal to 1, which means probability of finding the particle in the system equal 100%. Perform normalization of the wave function psi of x equal x squared over the interval 0 to k. So we are given a wave function that is not normalized, and we have to normalize this wave function. So the first thing we need to do, since the wave function is not normalized, we have to multiply the wave function by the normalization constant. We can choose any letter since it was not indicated in the question. So let's say our normalization constant n, then x squared. Now we are going to solve for this here. And we've been given an interval from 0 to k. So to find normalization, to normalize this problem, we take integral from 0 to k of the wave function squared, or squared in terms of x to dx. And the wave function now is nx squared. So integral from 0 to k nx squared all squared dx. It should be equal to 1. We are normalizing it. When it's normalized, when we evaluate this whole thing, it will give us 1. So now let's simplify this whole term right here to solve for the normalization constant. We are going to integrate. So let's do a quick revision on integration. If I am to integrate x to the power n, it should be equal to x the power increased by 1. And after that, I'll divide the whole thing by the power, which is n plus 1. So integrating x to the power 3 equal to x to the power 3 plus 1, 4, divided by 4, plus our integration constant. If I'm giving intervals from 0 to 1 to integrate the function x squared dx, now I'll first integrate this. So x to the power 2 plus 1, 3 divided by 3. So now evaluate it from 0 to 1. So doing so would be first, wherever I see x, I put 1 there. So 1 to the power 3 over 3, then minus, wherever I see x, I put 0 there. So 0 to the power 3 over 3. So simplifying this whole thing to give me 1 on 3. So that is how integration is done. So let's proceed. So now we are integrating this. So from 0 to k, squaring, expanding this whole term. So n to the power 2 is n squared Then x to the power 2 gives us x to the power 4. I just multiply this by that. So x to the power 4, the x equal 1. Now, since n is a constant, let's bring it out. So n squared integral from 0 to k x to the power 4, the x equal 1. Now, let's integrate this term. So 4, the power increased by 1. So x to the power 4 plus 1, 5, all divided by 5. Don't forget, we have a constant here, n squared multiplying. So now the interval from 0 to k, indicate them here. So this should be equal to our n squared is here, multiplying. We first put in our upper limit. Wherever we see x, we put k there. So k to the power 5, all on 5, minus, wherever we see x, we put 0 there, the lower limit. So x 0 to the power 5, all on 5, or multiplying. So now, this will give us n squared multiplied by k to the power 5, all on 5. Any number 0 to the power 0 is the same as 0, and 0 over 5 will make this whole term goes 0. So just as this, it should be equal to 1. So now we have n to the power 2 multiplying k to the power 5 all over 5 equal 1. So let's multiply both sides of the equation by 5. So this 5 will take care of that 5. So we are going to get n squared k to the power 5 equal 1 by 5, which is 5. We are looking for n squared. So let's divide both sides of the equation by k to the power 5. So doing so, k to the power 5, k to the power 5, this will take care of that. So we're left with n squared equal 5 over k to the power 5. So let's take square root of both sides. This will cancel that. So our normalization constant is now equal to 5 over k to the power 5. So this is our normalization constant, that if we multiply it by the wave function here, the probability density should be equal to 1. So now let's write our normalized wave function. Our normalized wave function, psi of x, is now psi of x equal n x squared, but we now know n, which is our normalization constant, to be square root of 5 over k to the power 5. So square root of 5, we have 5 over k to the power 5, or root, then the wave function, which is x squared, then x squared. So now this wave function is now normalized. So this is a normalized wave function. With the intervals given, if you want to prove that, you can take integral from 0 to k of this whole term here squared to c. You will get a value to be 1. That is how to prove that a wave function is normalized. Normalize the given wave function for a particle in a box, given that psi of x equal sine 2 pi x. So this wave function psi of x is not normalized, and we want to normalize it. So if the wave function is normalized, it should be in a form, let's say our normalization constant a should be multiplying the wave function psi 2 pi x, psi 2 pi x. So we first have to solve for the normalization constant. But we have not been given any limit. But we know that we are dealing with a path a particle in a box. For a particle in a box, there is zero chance outside of finding the particle. Outside the box, there's zero chance of finding it there. But inside the box, let's say there is one chance of finding the particle there. The particle has nowhere to go outside the box. It is in the box. So zero chance outside and one chance inside. So that should be our integration limit. So 0 to 1, we are integrating psi of x squared. So psi of x absolute squared. And this is the same as that over here. So from 0 to integral from 0 to 1 of a sine 2 pi x all squared dx should be equal to 1. So now let's simplify the expression. So a squared, we are going to get a squared integral from 0 to 1. Then sine squared, sine 2 pi x multiplied by, to the power 2 is going to give us sine squared 2 pi x dx equal 1. Since a is a constant, our normalization constant, we can bring it out. A squared integral from 0 to 1 sine squared 2 pi x dx equal 1. Now what do we do next? We want to integrate sine squared 2 pi x. To do so, we are going to use the reduced angle formula in trade. We know that sine squared theta equal 1 minus cos 2 theta over 2. So sine squared can also be written as 1 minus cos 2 theta. In this case, this whole thing is our theta. We are multiplying this whole thing by 2. So it's going to give us 2 multiplied by 2 pi x, which is 4 pi x. Cos 4 pi x, then all divided by 2 dx should give us 1. Now, this over 2 here is the same as, it's more like this term multiplying by half, then simplified to be over 2. So we can take half outside, factoring these 2 out. So we can get it to be a to the power 2 multiplied by half from 0 to 1. 1 minus cos 4 pi x dx equal 1. We just factored 2 out. So now we can simplify this as a squared over 2 integral from 0 to 1 minus cos 4 pi x dx equal 1. Now we want to integrate this. If we integrate a constant, let's say integrating 1 is going to give you x, 1x. 2 is going to give you 2x. 5 is going to give you 5x. That is if you are integrating. So integrating 1 gives us x minus. So integrating cos 4 pi x, what do we get? If you are integrating cos x dx, what you get is sine x. Integrating cos kx equal 1 over k, the term over here, 1 over k sine kx. Integrating sine kx equal 1 over k here minus 1 over k here multiplied by negative cos kx. So the whole 2 becomes minus 1 over k cos kx. So now let's apply this here. So here, the variable that we are working with is x. So anything here that is not part of that becomes our k, right? So 1 over 4 pi. So 1 over 4 pi. And then if we integrate cos, what do we get? We get sine. So sine of everything here. Sine 4 pi x. Then we bring in our limit from 0 to 1 to give us 1. There's no need to include the integration constant here. So at the end of the day, it will be of no use to cancel out. Now let's continue. So let's apply the limits. First of all, we put in the upper limit, which is 1. Then we subtract, first of all, let's put in the upper limit. Let's substitute the upper limit here. So we have a to the power 2 over 2. So we have x here. Wherever we see x, we put in 1, the upper limit. So 1 minus, wherever we see x, there's x here. So 1 giving us sine 4 pi all over 4x. 4 pi. The same as, you can write this term here like this. So then minus, we now put in the lower limit. We subtract that from that. So putting in the lower limit, x here, wherever we see x, we replace it by 0. So 0 minus, this can be written as sine 4 pi x here, which is 0 all over 4 pi. They are all multiplying a squared over 2. So another identity that you need to know is sine 4 pi equals 0. Sine pi equals 0. And then sine 0 equals 0. So those are the things you need to know when you are dealing with problems like this. So now we've solved our normalization constant to be root 2, and our normalized wave function. This was the wave function given to us, which we were supposed to normalize it. So after getting our normalization constant, then the normalized wave function psi bar of x equal the normalization constant multiplied by the original wave function that was given to us to be normalized. A particle in one-dimensional box of length L is described by the wave function psi of x equal sine n pi x over L for the interval from 0 to L. 0 is less than or equal to x, while x is less than or equal to L. So find the normalization constant n such that the total probability of finding the particle in the box is equal to 1. So in this problem, we've been given the interval from 0 to L, and we have to find the normalization constant. The wave function is not normalized. For it to be normalized, our normalized wave function, we should multiply the original function by the normalization constant. In this case, the question says we should call it n. We should call it n. So we multiply n by sine n pi x all over L. So now we proceed. Integral, the limit is from 0 to L. So integral from 0 to L of psi of x squared dx should be equal to 1. And now we know this psi of x is now, is it equal to n sine n pi x over L. So let's do that. So this is going to be n sine n pi x over L dx. equal 1, all squared here. So let's expand what is in the absolute sign or the bracket sign. So n to the power 2 gives us n squared, then sine to the power 2 gives us sine squared n pi x over L, the x equal 1. Integral from 0 to L. Since n is a constant, let's bring it out. The integral from 0 to L, sine squared n pi x all over L, the x equal 1. We are going to use the trig identities, the reduced angle formula, to simplify this expression. We have sine, if we have sine squared theta, it should be equal to 1 minus cos 2 theta over 2. So in this case, we can rewrite this as n squared integral from 0 to L 1 minus cos 2 theta. All this is theta, right? So we multiply it by 2. So 2 pi x, 2 n pi x. So let's bring n here. All over L, all over L, all divided by 2. The x should be equal to 1. Now we can factor this 2 out by multiplying this 2 right here is the same as this whole thing multiplying half. So if you simplify it, it's the same as dividing by 2. So we bring that half out. So n squared multiplied by half, integral from 0 to L 1 minus cos 2n pi x all over L, the x equal 1. So we can rewrite n squared over half and multiply by half as n squared over 2 integral from 0 to L 1 minus cos 2n pi x all over L, the x equal 1. So rewriting all this in this form, just simplifying this term here, n squared over 2. So now we integrate this term here. If you are integrating cos x dx, it gives you sine x. Cos kx dx, it gives you 1 over k here, sine kx. So let's see. In this case, integrating a constant 2 will give you the constant multiplied by the variable in concern. So if you integrate 1, you are going to get x. Integrate 2, you are going to get 2x. You integrate 3, you are going to get 3x, right? So now integrating 1 here gives us x minus integrating cos 2n pi x over L. What do we get? If we integrate cos, we get sine, right? So what we just did is that we are integrating a constant 1, then integrating this constant with respect to x, we get x. So integrating cos 2n pi x over L, if we have cos x, we are integrating it, we get sine x. But cos kx, integrating it gives us 1 over k. Whatever is here apart from the variable in concern, 1 over that, then sine kx. So here we have 2n pi x over L. So apart from the variable x, 2n pi over L. So 1 over this, 1 over 2n pi over L, sine, integrating cos gives us sine 2n pi x over L. Then we now bring in the limit from 0 to L equal 1. So now let's put in the limits. So n squared over 2. So firstly we put in the upper limit. Wherever we see x, we put L there. So x here, so L minus this 2 pi 2n pi over L can also be written as L over 2n pi. It's more like 1 over 2 over 3. It's also the same as 1 divided by 2 over 3. To take away with the division sign, you call 1 multiplied by with the reciprocal of this, so 3 over 2. So it just as turning this over, forgetting the 1. So wherever we see x, we put L there. There's x here. So sine n pi L divided by L. Then minus, we now put in the lower limit. So we have x here. Wherever we see x, we put 0 there. The lower limit is 0. So minus L over 2 pi, L over 2n pi, then minus this minus sign, L over 2 pi, this term here, which is the same as L over 2 pi, then sine 2n pi x, there is x there, so we put 0 there, the lower limit. Wherever we see x, we put 0 there, all over L. They are all multiplying n squared over 2. So the next thing you need to know is that if we have sine pi, it will give us 0. So sine n pi gives us 0. Sine 2n pi gives us 0. So now, looking at this term here, we have sine 2. We should have added 2 here. So there is 2 here. So sine 2n pi is 0. Sine n pi is 0. Sine pi is 0. We have sine 2n pi here. Definitely, this whole term will go to 0. And we have sine 2n pi here multiplying by 0 again. So this whole term will go to 0. 0 will have no effect on anything here. So we are left with L here. So the remaining terms here are n over 2 L equal 1. So we now solve for n, which is our normalization constant. That is what we are looking for. So multiplying both sides of the equation by 2 gives us n to the power 2, L equal 2. So divide both sides by L, divide both sides by L. So we are going to get n squared equal 2 over L. Taking square root of both sides, we give our n, our n would be equal to 2 over L square root, or under square root sign. That is our normalization constant. Now that we are done with our normalization constant, we just multiply the wave function that was given to us by the normalization constant. And that will be our normalized wave function. This is the wave function that we are normalizing. Sine of x equals sine n pi x over L. Now that we know our normalization constant to be square root of 2 over L, our normalized wave function would be equal to square root of 2 over L, square root of 2 over L, multiplying the function, original one that was given to us, sine n pi x over L. So if we integrate this wave function, over the interval from 0 to L, you should be getting 1, indicating that the wave function is normalized. Normalize the wave function psi of x equal x into bracket L minus x for a particle in a box with length L. We are looking at the 100% probability of finding a particle in a box of length L. For a box of length L, we know that the probability of finding the particle outside the box is going to be 0%. And the chances of finding it in the box is to L. So our limit of integration is 0 to L. And the probability of us to find the particle, 100% probability of finding a particle in the box equal integral from 0 to L. That is our limit of integration of absolute psi of x squared dx equal 1. But in this case, the normalization constant has to be included. We need a constant that when we multiply it by this wave function, it will be normalized. It will give us 100% probability of finding a particle in a small space. So we have to include the normalization constant. So let's say our normalization constant is n. So the wave function should be of this format. When it is normalized, nx, just multiply n by it, L minus x. So now we are going to take this wave function and solve for the normalization constant. So integral from from 0 to L equal psi of x squared. When normalized, this is what we are supposed to get. So we are going to take this absolute square of that because we want to solve for the n, the constant that we multiply by this to make it normalized or to make it useful for describing physical systems. All squared dx equal 1. So anytime we are talking about a particle in a box, you should know that there is 0 chance of finding the particle in the box, outside the box, and there's L chance of finding the particle in the box. If you are not given the length of the box, then you can decide to choose 1, meaning, there is 100% of finding the particle in the box. So now let's square whatever is under the absolute sign. So squaring this whole thing, they've raised to the power 2. So n to the power 2 gives us n squared. X to the power 2 gives us x squared. All into bracket, L minus x to the power 2 dx equal 1. Since n is a constant, let's factor it out. So integral from 0 to L n squared x squared into bracket L minus x to the power 2 dx equal 1. If we have a term a minus b to the power 2 and we want to simplify it, we square the first term a to the power 2 and we multiply 2 by a by minus b, giving us minus 2ab, and we score the last term b squared. So let's apply this idea here. So we are going to have n squared integral from 0 to L, x squared, so L to the power 2 L squared plus 2 multiplied by L multiplied by minus x, that will give us minus 2 Lx plus negative x to the power 2, giving us x to the power 2 dx equal 1. So now let's expand the bracket, multiplying 2 by x squared. So we are going to get n squared integral from 0 to L. X squared multiplied by L squared gives us L squared x squared. X squared multiplied by 2Lx minus 2Lx to the power 3. Since of that they are of the same basis, we add their powers. So x squared multiplied by x squared gives us x to the power 4. So dx should give us 1. So now integrating, if I have x to the power 4 and I'm integrating, it's going to give me x to the power 5 over 5. The power increased by 1 divided by, everything divided by the increased power. So now let's do the same here. So we are going to get n squared. So we are integrating with respect to x. So we are going to get L squared. X to the power 2 gives us x to the power 3. Then we divide everything by 3 minus 2L x to the power 3, integrating it gives us L to the power x to the power 4 all over 4 to plus x to the power 4, integrating it gives us x to the power 5 over 5. And our limit of integration is from 0 to L equal 1. So now let's introduce our limit of integration. First, we start with the upper limit. So n squared limit. So wherever we see x, we replace it by L. So we have L to the power 2, x to the power 3 becomes L to the power 3 all over 3. Here we have minus 2 over 4. 2 can cancel out. Here 1, 2 goes here 2. So we can just write 1 Lx, which is the same as Lx. But we are replacing x with L. So L to the power 4 all over 2 plus x to the power 5 becomes L to the power 5. L to the power 5 all over 5 into bracket minus. We now put in the lower limit. Wherever we see x, we replace it by 0. So L multiplied by x to the power 0, L to the power 2, multiplied by x 0 to the power 3, all over 3 minus L x to the power 4. We've simplified this place to be 1 over 2. So all on 2 plus x to the power 5 becomes x to the power 0 to the power 5 all over 5 equal 1. So this whole term here, this becomes 0, this becomes 0, this also becomes 0. So now we can just write this out in terms of this. So n to the power 2, L to the power 2 multiply L to the power 3 gives us L to the power 5, right? L to the power 5 over 3. L multiplied by L to the power 4 gives us negative L to the power 5 over 2 plus L to the power 5 over 5. Since this whole term is 0, so you can just equate it to 1. So now let's factor L to the power 5 out. So n squared L to the power 5 into bracket. This place becomes 1 over 3 minus 1 over 2 plus 1 over 5 equal 1. So let's add whatever is in the bracket. So we are going to get 1 over 30. So n squared L to the power 5, 1 over 30 and equal 1. So multiplying both sides by 30, both sides of the equation by 30, this will take care of that. And then we are going to get n to the power 2, L to the power 5 equal 30. And now we want to divide both sides of the equation by L to the power 5. So L to the power 5. So this will take care of that. We are going to get n to the power 2, n to the power 2 equal 30 over L to the power 5. So taking square root of both sides, this will cancel that. N is going to give us 30 over L to the power 5, L to the power 5 for the square root sign. So this now is our normalization constant for this question. The question asks us to normalize the wave function. To normalizing the wave function, the question didn't indicate any letter for us for the normalization constant, and we decided that n should be our normalization constant. We just multiply it by the given wave function and take the absolute square of that and integrate with the given limits to get our normalization constant. Now we can go ahead and write the normalized wave function as this. We were looking for a constant that when multiplied with the wave function would be able to describe a real system. It won't give us a negative probability, but a positive 100 probability of finding a particle in the box, because the particle is in the box. That is if it exists in the box. So now we are going to write our normalization constant and then x to bracket L minus x. So square root of 30 over L to the power 5 multiplying x into bracket L minus x. So this is our normalized wave function. Find the normalization constant A of the wave function below and state the normalized wave function. The wave function is given to us as psi of x equal a sine 2x if the interval is from negative pi to positive pi. And the wave function is 0 if elsewhere. In actual sense, the wave function is 0 if elsewhere. It means if we integrate from 0 to negative pi and from negative pi to positive pi and from positive pi to 0. If we integrate from here to that, we are going to find a 0, the wave function will be 0 there. It can't describe any probability over there. And here too is going to give us 0. So our main focus is on this limit. The particle must be there if it exists. So that is it to know about this whole problem. Now let's start solving. So in this case, the normalization constant has already been introduced into the wave function. So there's no need for us to introduce a normalization constant again. We just have to take the absolute square of that and integrate with the given limit, negative pi to positive pi. So to normalize this wave function, we need a normalization constant, a value to multiply by the wave function, which is a here. So we are initially going to solve for a, integrating from negative pi to positive pi. So psi of x or squared, the x equal 1. And our psi of x is this term here. So this should be giving us negative pi to positive pi a sine 2x absolute squared the x equal 1. So now let's go ahead and simplify whatever is under the term here. So a to the power 2 gives us, since a is a constant, I'm going to bring it out. So let's try solving it step by step. So a to the power 2 gives us a squared, then sine 2x to the power 2 gives us sine squared 2x, and then the x equal 1. Now a is a constant, I'm going to bring it out. So a squared into bracket, integral from negative pi to positive pi sine squared 2x, the x equal 1. So we are going to use the angle reduction formula in trigonometry to evaluate this. Sine squared theta is equal to 1 minus cos 2 theta over 2. So let's try simplifying this. So this sine squared now becomes, let's say, a squared integral from negative pi to positive pi minus 1 minus cos 2 theta. In this case, this is our theta, and we are going to multiply this by 2. So 2 multiplied by 2x gives us 4x, all divided by 2, the x equal 1. Since wave functions are usually in the sign and the form, this trig identity form, it is easier to keep them in memory in order to help your problem solving skills. To improve your problem solving skills. So now the next thing we want to do is to factor half out. This is the same as half multiplying this to get 1 over 2 here. So we can just factor half out. So a to the power 2 multiplied by half, integral from negative pi to positive pi of 1 minus cos 4x the x equal 1. So this one becomes a squared over 2 integral from negative pi to pi positive pi 1 minus cos 4x the x equal 1. So now let's integrate the term. So a squared over 2. If I'm integrating cos theta, it's going to give me sine theta. But if I'm integrating cos k theta, it's going to give me 1 over k sine k theta. So we are going to apply that idea here. So we have 1, integrating 1, a constant. If I'm integrating 2 with respect to x, it's going to give me 2x. Integrating 5 with respect to x is going to give me 5x. Integrating 1 is going to give me 1x, which is the same as x. So this place becomes x. So minus, integrating this, we have a constant here. So 1 of that constant, for we are integrating cos, then it now becomes sine of everything here. The limit of integration is from negative pi to positive pi. So give us 1. So now we are going to put in our limit of integration, starting with the upper limit, which is positive pi. So a squared over 2. So wherever we see x, we put in pi there. Pi minus sine 4x, which is sine 4 pi. You can just divide this whole thing by 4 into bracket. Then minus bracket, we put in our lower limit, which is minus pi. Wherever we see x, we put it minus pi over there. So x, which is minus pi, minus sine 4x, which is sine 4 negative pi. So this will become negative 4 pi. All on 4, close, equal 1. So another identity that you need to know, because solving problems like this usually involve trig, sine or cos, just know the simple identities and you'll be good to go. So we know that anytime you see sine pi, it gives you 0. Sine constant plus pi gives you 0. Sine anything by pi basically gives you 0. So sine 4 pi gives you 0. So we have sine 4 pi here giving us 0. So this term becomes 0. And we have sine 4 pi here. This term becomes 0. So we are going to have a to the power 2 over 2 into bracket. This remains here pi. And what else do we have here? Negative pi giving us positive pi. So positive pi into bracket equal 1. So in this case, pi plus pi gives us 2 pi. So a squared over 2 multiplying 2 pi equal 1. 2 can take care of 2, and then we are left with a squared pi equal 1. Dividing both sides by pi, this cancel that. Then our a squared equal 1 over pi. So taking square root of both sides, our a, which is the normalization constant, going to give us square root of 1 is the same as 1, square root of pi. So this is our normalization constant. So this is what we need to multiply to the wave function that can make the wave function used to predict system. So now we were asked to find the normalization constant, which is a, and this is our normalization constant, and normalize the wave and state the normalized wave function. So the normalized wave function is now stated as psi of x equal a sine 2x, and our a now is 1 over square root of pi. So 1 over square root of pi, then sine 2x. So this is a normalized wave function. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.